You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Brian Keating. Dr. Keating is a physics professor at the University of California, San Diego, and the director of the Simons Observatory, specializing in the study of gravitational waves created during the early stages of the Big Bang. Dr. Keating is also a pilot and is the recipient of the 2007 Early Career Award for scientists and engineers for his work with BICEP.
And we're back with Dr. Brian Keating. Now, Brian, you are connected up with the Simons Observatory and looking at the CMB. Give us an overview of what you're doing.
Yeah, the CMB, of course, is the oldest light in the universe, and as such, it really behooves us to look and try to mine it to whatever extent we can. Nature gives us so few signals with which to understand her magnificent tapestry that we spend a lot of time being as efficient as possible with each bit of information we receive. The Simons Observatory was a project that my collaborators and I proposed to the Simons Foundation, which has supported my research for about 11 years now. And that was a project comprised of 4 telescopes with a primary focus on unraveling the origin of the universe, if indeed inflation was the culprit, providing the spark, if you will, that ignited the Big Bang, with 3 telescopes not dissimilar from the BICEP instrument that we talked about when I was on Event Horizon last time, as well as another telescope, 6 meters in diameter, which is more than 10 times the diameter of these small aperture telescopes, these 3 inflationary science dedicated instruments. The large aperture telescope, a single instrument, has 2 enormous 6 meter, 20 foot diameter mirrors that are used to obtain an extremely high resolution image of these microwave photons that come to us in all directions that we call the cosmic microwave background. And the goal of the large aperture telescope is to really make the finest, most detailed image of various properties of the early universe and its subsequent evolution to this very moment via a series of science campaigns that it is capable of doing. And those involve understanding the masses of neutrinos, which manifest themselves on the smallest scales in the microwave background, but also looking at the effect of dark energy, this accelerated expansion of the universe's, if you will, scale. With every day that passes, the universe is expanding a little bit more. And not only that, its expansion rate is increasing with time. And that has enormous implications, not only for our present understanding of what's going on in the universe, but also perhaps on the very distant future of the universe, where it may come to a rather violent end in what's called a big rip. And so understanding the property of the microwave background to reveal the essence of this particular medium known as dark energy is a crucial goal of the Simons Observatory Large Aperture Telescope. And the last kind of major project for the large aperture telescopes, in addition to looking at many, many tiny galaxies and their imprint and what's called the Sunyaev-Zeldovich effect, and making catalogs of galaxy clusters in a very unique and interesting way, is to perhaps measure local objects. And this, by local, I don't just mean, in a galaxy far, far away. I mean in our solar system. And it may be that there is actually a 9th planet. So, we've demoted the planet Pluto to be called a dwarf planet or a minor planet. But there are still many, many reasons to think of objects on the outer limits of our solar system, perhaps located beyond or within the Kuiper Belt itself, this object called Planet 9. And this planet is so far has very maybe tantalizing hints of evidence for its existence. But because it will have a very low temperature that is associated with approximately the same temperature as the cosmic microwave background radiation, perhaps maybe 10 times hotter, if you will. If you can call 40 degrees above absolute zero hot, then it will emit in a wavelength range that we can detect with the instruments that we built for a completely different purpose. And that is to measure the existence, or perhaps set limits on the existence, of multiple such objects. And there are objects that are thought to exist, that we know to exist from other instruments. And we're going to kind of try to zoom in on these objects and perhaps place very strong limits on the existence of such objects that change with position. The very notion of a planet in the Greek language is something that wanders against the fixed stars. So one of the key science goals for the Simons Observatory is to set limits on phenomena such as that.
Now, I have to ask, what about SETI? I mean, is there any usefulness in this area for SETI searches or technosignatures or anything like that?
That's a very fascinating question. And it's not part of our, core science goal, but we do kind of have these as an all-encompassing catch-all terminology in what we call the unexplored millimeter transient sky. So things that go bump in the night, if you will. These could be things that are associated with what are called gamma ray bursts that have a radio microwave frequency analog. These could be objects that are fast radio bursts, which we don't understand exactly what's happening when supermassive black holes suck in material such as stars nearby and create perturbations to the black hole's event horizon. Not your event horizon, but the black hole's event horizon can be perturbed. And in principle, that can release the pent-up charge and matter and mass within the event horizon's outer limits, causing a burst of energy, some of which may make its way to our telescopes in the form of microwave wavelength radiation that we can then detect. And because we have this unique polarization capability, we can probe the nature of these precious photons in great depth and unprecedented accuracy. Now, I secretly will be very interested to know if some of the bursts that we see in the microwave or millimeter regime of the sky, they might be actually potentially useful for a technosignature that could potentially be something that we should not rule it out based on prejudices or biases. And in fact, some have suggested, and I've discussed this with others before, that it might be natural for an alien civilization to want to broadcast its existence to the rest of the universe and use the microwave background as sort of a light post, a lamppost, if you will. In other words, they will know that any cosmologist working in this epoch of the universe's history will know, once they have the technological sophistication to measure the microwave background, they'll know where it peaks. They'll know the wavelength range in which to look and point their telescopes. And they might say, well, let's flood that channel with spam or with our broadcasting our existence. And in so doing, that may be a very fruitful way for them to get attention. Now, I can't speculate on why they would want to do such a thing. I'm just a simple cosmologist. But it may be something that we should not rule out as a potential serendipitous discovery. And as you know from my book, Losing the Nobel Prize, I think that those serendipitous discoveries are among the most important and exciting discoveries in all of science, and the ones that you essentially don't expect. But as I also say, serendipity is pretty hard to plan on.
Absolutely, but it has changed the world many, many, many times.
That's right, including the discovery of the cosmic background itself, which was discovered serendipitously.
Now, with the Simons Observatory, looking for outer solar system objects, what's the smallest thing you think you could see? Would you see objects like, for example, these minor planets out there? I mean, could you discover more of those? Do you have that kind of resolution?
Yeah. So what happens with microwave telescopes is that anything that has a temperature, anything that is made of matter, even dark matter, will have the potential to emit a thermal signal. You can't avoid, as a consequence of thermodynamics, you can't avoid the emission of what's called black body radiation. And so what we are limited to is how sensitive we can build our detectors at their location on these high volcanic plateaus in northern Chile in its Atacama Desert, where we are building, currently pouring concrete as we speak at this most vast, remote, inaccessible region of the Earth's surface at 17,200 feet above sea level. And what we're trying to do is make use of every photon that comes to us. Let no photon be wasted is our motto. And so we build exquisitely sensitive detectors with massive telescopes, 6 meters in diameter, that has something like 9 times the collecting area of the Hubble Space Telescope. And these instruments will certainly be capable of making unprecedented measurements of the microwave background, a resolution that Hubble would laugh at. But nevertheless, the resolution that we're looking for is sort of at what's called an arc minute, so roughly twice the diameter of Saturn or something like that. But that is sufficient to measure, as long as you have ultra-sensitive detectors, the heat emission from these objects. Even objects as speculative as Planet 9 at distances, perhaps 10,000 times farther away than Saturn, because our detectors are so sensitive, and these things aren't at absolute zero. They're actually 10 times hotter than the CMB, which we already detect with fantastic parts per million accuracy. So this is a challenge very well suited. The question that we have, John, is whether or not these things exist. And it's also a question that we ask ourselves when we study the main core science goals of the Simons Observatory. We don't know for sure that inflation took place. And so we may be forever setting limits on the existence of such things. But as with the case of setting limits on the origin of the universe and on the existence, perhaps, of violation of closely held beliefs about the laws of nature, sometimes that's all you can do, is rule out everything else and exclude things from being true. And hopefully what you're left with is a core essence of what we know about the universe.
Now, the CMB cold spot, the famous cold spot, are you going to be looking into that?
Absolutely. Yeah. So have you been looking at our science proposals here, John? Because these are exactly some of the things that we're interested in looking at. Turns out this CMB cold spot, which is this anomalous effect. But again, anomalies are things to look deeper into, because they may be the cracks that let light in to shed new light onto physics that was heretofore unexplored. And in the case of the CMB cold spot, there are many, many conjectures as to what it may be, but it was noticed because it is an anomaly. It's something strange. It's something that doesn't belong if what's known as the cosmological principle holds. Now, the cosmological principle is an allied concept with the Lorentz invariance that we talked about earlier. The cosmological principle suggests that the universe on its largest scales is isotropic, meaning it looks the same no matter which direction you look in, and it's homogeneous. It's made of the same material. It has the same basic, density, matter distribution, etc., on large enough scales. Obviously, that doesn't hold on the scale of a planet, and it's not until you go beyond the size scale of a galaxy cluster that it holds. But as far as we know, this principle, the cosmological principle, holds over the whole universe. So the CMB cold spot throws a wrench into this notion that the universe should be very, very much immune to fluctuations that single out a particular direction, as does the CMB cold spot. So in fact, it's a fascinating thing to look at. So far, as you say, it's a cold spot, which means that we only know about it via its temperature, anomalous temperature behavior. But now, with the Simons Observatory and its high-resolution telescopes, we are able to zoom in on it and also look at it using the additional information that we will glean from having polarization measurements as well. And so we'll ask the question, is it as anomalous in its polarization behavior as it is in its temperature behavior? In which case, it would be a very, very surprising revelation if that is anomalous in both ways. So stay tuned for that. That is one of our very, very interesting science goals.
Now, that is interesting, because if that could allow you to characterize what it actually is. And there have been some really interesting ideas advanced on what it could be due to. As I recall, one of them was we bumped into another universe and things like that.
That's right. That's right. So the one of the allied theories that comes concomitantly with inflation is the expected existence of the multiverse, which we talked about in our previous conversation. Do bubble universes exist? If that's true, there may be in this field of research multiple avenues to divine the existence of the multiverse. It could be indirectly through the observation of B-mode polarization, this curling, twisting pattern of microwaves. That's the subject of my book and of the BICEP experience, and much of some of the motivation for the small aperture telescopes in the Simons Observatory. But there's another way we could get effectively direct evidence. In other words, the indirect evidence would come from the B modes that we would potentially see, and the indirect evidence would come from, and the direct evidence would come from a collision with the bubble universe, causing this anomalous behavior. And so both of these ways of approaching different fields, observation that would come to the same conclusion, would give us stronger credence in the underlying existence of the multiverse, which remains one of the most controversial aspects of modern cosmology. So the more ways to probe it, the better.
One other anomaly regarding the CMB that I hear about is the so-called axis of evil problem, where the CMB above the plane of the solar system is a little bit different temperature than below. Is that the right way to characterize it? I mean, is it really as interesting as it seems to be, or is it maybe not really real?
That is a very interesting question. It is real in the sense that, there is data. There are data points that suggest the existence of it being verifiable. However, there could always be stronger confidence that we must get, and as well as measuring the signal in multiple different techniques. So polarization, different frequencies, et cetera. Those are ways that we as scientists come to consensus. Scientists don't look for some authority. Oh, Einstein said that there were waves of gravity, therefore we believe it. No, we have evidence for it, because Einstein also thought many things that were wrong as well. So we don't rely on authority. We don't rely on consensus either. We rely on consensus that does get built up when multiple different aspects of science point to the same conclusion. So, for example, we believe in anthropocentric global climate change because we can look at ice cores, we can look at paleobotany, we can look in many different ways, geochemistry, and so forth. So there are many different scientific fields that are completely disparate. They don't have correlations between their prejudices and biases, and therefore you can have great confidence in such an observation. We'd like to do the same thing with things like the multiverse, like the axis of evil, like the cold spot. The challenge is that there aren't so many ways to probe anomalous microwaves other than using microwaves themselves. And so in this case, we have to exclude the other culprits that could produce such a behavior, and some of them range from the presence of our own solar system within our galaxy. Obviously, what we call galactic foreground emission could contribute to this. And we have to test and tease the data in as many different ways as possible to first see if the data are consistent in these different cuts and analysis mechanisms. We have to remove our bias from these measurements in a reproducible fashion. And then we have to try to follow up in as many different frequencies and polarizations over as long a time scale and with different experimental teams looking at it. So for now, it's been primarily confined to spaceborne observatories. And for good reason, we expect that the Simons Observatory will both be able to highlight and perhaps shed light onto the axis of evil, the cold spot, inflation, the multiverse, Planet Nine, but we're going to not be the final word. We're always going to need to look for consensus from different aspects of cosmology and astrophysics to confirm, or, as happened in BICEP 2 episode and losing the Nobel Prize, refute. And that's part of the healthy scientific process.
Now, I have one special question here, and something piqued my interest. So this is just me asking this question. You are the first person in the entire astronomy world that I'm aware of that has found a use for a drone. Tell us about the drone.
So, it's funny, John. I was talking the other day to my wife, and then all of a sudden I heard a drone flying around the house. And I said, no drone flying in the house. And I heard my mom screaming, no playing ball in the house. And, how much has the world changed since we were kids, right? And so I've always wanted to use drones, and I've always been fascinated by them. I own some of the earliest ones that are, collecting dust, but I can't throw them out because they cost $1,000, 15 years ago when they first came out. And I'm just, you could replace it now with the drone my kid got for his birthday. However, we have found a use for drones at the Atacama Desert site that is really going to hopefully replace a $100 million CubeSat or a similarly expensive project that heretofore would have been needed to launch into space with all the concurrent costs and complications and safety regulations, et cetera. So instead of going to those Herculean efforts, for which I have made applications to NASA and been rejected every time, now we decided we're going to choose ourselves and do it ourselves. And we figured out a way to use a drone, a commercial drone with a good payload, modified it because typical drones are built for most consumers, operate close to sea level. They don't operate at 17,200 feet above sea level in challenging Atacama Desert. And so we've already played around with drones and used them for photographing the site, mapping out the site. And so my colleague Rolando Dunner at the University, Pontifical University in Chile, he came up with this amazing idea to mount a particular type of microwave source to a drone and then fly that over the Simons Observatory site and use it for the most important phenomena that we have, and that's called calibration. So if you ever think about it, when you go to a store and you buy a pound of coffee, how do you know you got a pound of coffee? Well, it turns out for most of the last, 5 or so decades, it was actually traced to a standard weight of platinum, I believe, kept somewhere in Colorado and somewhere in Paris. And every other measurement on Earth was referenced to that standard kilogram. And then from that, you can get what the pound is. That's how you know you're getting what you pay for. It's called calibration. You have to calibrate your scales. You have to calibrate your instruments. How do you know what a 9-volt battery is? How do you know you're not getting an 8-volt battery? It's calibrated to fundamental physical phenomena. With the cosmic background radiation, it's very difficult to calibrate not only the temperature of a source, but also its polarization. And so what we have found is that we must replace the natural sources of calibration that we might otherwise use, say like liquid helium, as Penzias and Wilson did when they discovered the cosmic microwave background in 1965. We're going to replace that with an artificial calibrator. In this case, it's a radio frequency or microwave generator mounted to a drone flown 400 feet above the Simons Observatory, so close to 18,000 feet, where you're flying above anything other than commercial airliners. At least it's above that altitude. It's above half the atmospheric pressure that you feel at sea level, so it's very hard to breathe. The drones have to work really hard. They have short battery lives. It's an amazing and fun project as an engineering perspective on making a fundamental cosmic observation that may reveal the violation of our most closely held beliefs about the universe. So it's a really fun project to be involved with.
Yeah, that's just absolutely amazing. Tell us about your YouTube channel.
Well, it's thanks in part to you, John, that I've become inspired to share my love of the cosmos with the general public. And it's become somewhat of a mission. And some of my colleagues are getting annoyed at me because I've basically been hinting that I think it's almost, I'll say it to you, I think it's almost an obligation, maybe even a moral obligation that we have to our fellow citizens that pay our salaries. I'm a state employee of the great state of California. I've been supported by National Science Foundation, by the U.S. government, by NASA. My whole career has been dependent on the generosity of United States taxpayers. And for us to keep our discoveries private and not share access to fellow scientists, I felt was wrong. And so what I decided to do during the pandemic, I was inspired to bring kind of a form of what we call in academia a colloquium, a seminar, but do it with scientists, some cases live, where we have, say, Sir Roger Penrose, right after he won the 2020 Nobel Prize. I had him live on Dr. Brian Keating, my YouTube channel, and Into the Impossible, my podcast. And I took questions and answers from the audience. And it's really delightful to have somebody who might be inspired by Sir Roger from a live conversation, which Sir Roger inspired me back in 1989 when his famous book, The Emperor's New Mind, came out. He inspired me to not only want to become a scientist, but someday share it as a writer, as a popular science writer, if you will. So I would have died for the opportunity in 1989 to somehow talk to him. And I realized now is the time. We can do it. We can flatten and make more democratic the opportunities for people young and old to converse with the universe of brilliant minds that I am honored to have as guests on my show. So I've had a great deal of fun with this, and it's led to many other projects, including projects such as the first audiobook ever made of Galileo Galilei's books. I'm working on that with Nobel Prize winner Frank Wilczek, Carlo Rovelli of 7 Brief Lessons in Physics, and many other phenomenal scientists to bring these words to light. And it would not have happened, A, if you didn't inspire me, but if there wasn't this medium, this technology that we have to bring science to the people that enable us to have so much fun with our jobs. And this is my obligation, I feel, but it's also my greatest pleasure.
And you never know who you're going to inspire. I think about that too, because what I'm really doing with Event Horizon and my original channel, I'm making the content that 14-year-old me in 1989 wanted to see and didn't have.
Yes.
So I'm just that's what effectively what we do. It's mind-blowing, but somebody's going to become a scientist after watching this. Very, very, very humbling when you think of it that way.
It is. It's an awesome responsibility, but it's one I take just such delight in. As you say, somebody inspired us. And the last thing maybe to leave you with, John, is something that I learned from one of my teachers, that in Russian, the word scientist means one who was taught. And to me, that means we have an obligation to be teachers as well, such that the grand tapestry of science can play out far into the deep future of Earth.
All right, Brian, we are out of time. Thanks for visiting with us today, and we'll do this again sometime, especially if there's news about the CMB coming out.
I'm always at your service. Thank you guys so much for the service you do for the entire multiverse.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gauthier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. And be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?